What I hope to do in this video is prove that if a function is differentiable at some point c, that it's also going to be continuous at that point c. But before we do the proof, let's just remind ourselves what differentiability means and what continuity means. So first, differentiability. Differentiability. So let's think about that first. And it's always helpful to draw ourselves a function. So that's our y-axis. This is our x-axis. And let's just draw some function here. So let's say my function looks like this. And we care about the point x equals c, which is right over here. So that's the point x equals c. And then this value, of course, is going to be f of c. And one way that we can find the derivative at x equals c, or the slope of the tangent line at x equals c, is we could start with some other point, say some arbitrary x out here. So let's say this is some arbitrary x out here. So then this point right over there, this value, this y value, would be f of x. This graph, of course, is a graph of y equals f of x. And we can think about finding the slope of this line, this secant line between these 2 points, but then we can find the limit as x approaches c. And as x approaches c, this secant, the slope of the secant line, is going to approach the slope of the tangent line, or it's going to be the derivative. And so we could take the limit as x approaches c, of the slope of this secant line. So what's the slope? Well, it's going to be change in y over change in x. The change in y is f of x minus f of c. That's our change in y right over here. And this is all a review. This is just one definition of the derivative, or one way to think about the derivative. So it's going to be f of x minus f of c. That's our change in y, over our change in x, which is x minus c. It is x minus c. So if this limit exists, then we're able to find the slope of the tangent line at this point. And we call that slope of the tangent line, we call that the derivative at x equals c. We say that this is going to be equal to f prime of c. All of this is review. So if we're saying, one way to think about it, if we're saying that the function f is differentiable at x equals c, we're really just saying that this limit right over here actually exists. And if this limit actually exists, we just call that value f prime of c. So that's just a review of differentiability. Now let's give ourselves a review of continuity. So the definition for continuity is if the limit as x approaches c of f of x is equal to f of c. Now this might seem a little bit, it might pop out to you as being intuitive, or it might seem a little, well, where did this come from? Well, let's visualize it, and then hopefully it'll make some intuitive sense. So if you have a function, so let's actually look at some cases where you're not continuous, and that actually might make it a little bit more clear. So if you had a point discontinuity at x equals c, so this is x equals c. So if you had a point discontinuity, so let me draw it like this actually. So you have a gap here, and when x equals c, f of c is actually way up here. So this is f of c, and then the function continues like this. The limit as x approaches c of f of x is going to be this value, which is clearly different than f of c. This value right over here. If you take the limit as x approaches c of f of x, you're approaching this value. This right over here is the limit as x approaches c of f of x, which is different than f of c. So this definition of continuity seems to be good, at least for this case, because this is not a continuous function. You have a point discontinuity. So for at least in this case, this definition of continuity would properly identify this as not a continuous function. Now you could also think about a jump discontinuity. So let's look at this. And all of this is hopefully a little bit of review. So jump discontinuity at c, at x equals c, might look like this. Might look like this. So this is at x equals c. So this is x equals c right over here. This would be f of c. But if you tried to evaluate the limit as x approaches c of f of x, you would get a different value as you approach c from the negative side. You would approach this value. And as you approach c from the positive side, you would approach f of c, and so the limit wouldn't exist. So this limit right over here wouldn't exist in the case of this type of a jump discontinuity. So once again, this definition would properly say that this is not, this one right over here is not continuous. This limit actually would not even exist. And then you could even look at a function that is truly continuous. If you look at a function that is truly continuous, so something like this, that is x equals c. Well, this is f of c. This is f of c. And if you were to take the limit as x approaches c from either side of f of x, you're going to approach f of c. So here you have the limit as x approaches c of f of x indeed is equal to f of c. So it's what you would expect for a continuous function. So now that we've done that review of differentiability and continuity, let's prove that differentiability actually implies continuity. And I think it's important to kind of do this review just so that you can really visualize things. So differentiability implies this limit right over here exists. So let's start with a slightly different limit. Let me draw a line here actually. Let me draw a line to just show we're doing something different. So let us take the limit as x approaches c of f of x minus f of c, of f of x minus f of c. Well, can we rewrite this? Well, we could rewrite this as the limit as x approaches c, and we can essentially take this expression and multiply and divide it by x minus c. So let's multiply it times x minus c, and divide it by x minus c. So we have f of x minus f of c, all of that over x minus c. So all I did is I multiplied and I divided by x minus c. Well, what's this limit going to be equal to? This is going to be equal to, it's going to be the limit, and I'm just applying the property of limit, I'm applying a property of limits here. So the limit of the product is equal to the same thing as a product of the limits. So it's the limit as x approaches c of x minus c times the limit, let me write it this way, times the limit as x approaches c of f of x minus f of c, all of that over x minus c. Now what is this thing right over here? Well, if we assume that f is differentiable at c, and we're going to do that. Actually, I should have started off there. Let's assume, because we wanted to show that differentiability improves continuity. If we assume f differentiable at c, well then this right over here is just going to be f prime of c. This right over here, we just saw it right over here. That's this exact same thing. This is f prime of c. And what is this thing right over here? The limit as x approaches c of x minus c? Well, that's just going to be 0. As x approaches c, this is going to approach c minus c. It's just going to be 0. So what's 0 times f prime of c? Well, f prime of c is just going to be some value. So 0 times anything is just going to be 0. So I did all that work to get a 0. Now, why is this interesting? Well, we just assumed that if f is differentiable at c and we evaluate this limit, we get 0. So if we assume f is differentiable at c, we can write the limit, I'm just rewriting it, the limit as x approaches c of f of x minus f of c, and I could even put parentheses around it like that, which I already did up here, is equal to 0. Well, this is the same thing. I could use limit properties again. This is the same thing as saying, and I'll do it over here. Actually, let me do it down here. The limit as x approaches c of f of x minus the limit as x approaches c of f of c is equal to 0. The limit of the difference is the same thing as the difference of the limits. Well, what's this thing over here going to be? Well, f of c is just a number. It's not a function of x anymore. It's just f of c is going to evaluate to something. So this is just going to be f of c. This is just going to be f of c. So we have the limit of f of x as x approaches c minus f of c is equal to 0. Well, just add f of c to both sides, and what do you get? Well, you get the limit as x approaches c of f of x is equal to f of c. And this is the definition of continuity. The limit of my function as x approaches c is equal to the function, is equal to the value of the function at c. This means that our function is continuous at c. So just a reminder, we started assuming f differentiable at c. We use that fact to evaluate this limit right over here, which we got to be equal to 0. And if that limit is equal to 0, then it just follows, just doing a little bit of algebra and using properties of limits, that the limit as x approaches c of f of x is equal to f of c. And that's our definition of being continuous at the point c. So hopefully that satisfies you. If we know that the derivative exists at a point, if it's differentiable at a point c, that means it's also continuous at that point c. The function is also continuous at that point.